step that we're going to talk about is, well, programming for heterogeneous architectures. That is to say that we're getting away from just programming on the CPU, and we're going to also put to work the GPU. At this point in our roadmap, we've covered the idea of parallelization, use threads and locking and that kind of thing, and do it wisely and do it well, and we get a good speed up. It gets a little harder after that to improve single-thread performance, but we've spent some time talking about it, and one of the ways that we could do that is with SIMD, and one of the ways that we could do that is with getting out of the way of the compiler and letting it do its thing. Okay, now we've reached the point where actually those aren't quite sufficient anymore, and we have to think about doing something a little more exotic, and that takes us to programming with the GPU. We're going to program using CUDA. This is the NVIDIA Compute Unified Device Architecture. It is usable on NVIDIA GPUs, and unfortunately not on GPUs from other manufacturers. To the best of my knowledge, at least at the time of recording, all of the ECE servers with GPU cards in them have NVIDIA cards. So in that regard, we should be okay. And previously, we used to do this in OpenCL, which was cross-platform, but that's no longer the case. The RTX 3080 not available at the time of writing. This is an ongoing thing in the back half of 2020, and people probably sell pictures of them on eBay or like the empty box for some money. I can't really imagine that things are going to get any better immediately, and it'll probably be a few months at least before the stock situation has improved. But we'll hope for things to get better. All right, another thing that we might see that when we talk about using the GPU is SIMT, which is slightly different from the SIMD that we talked about earlier. It's single instruction, multiple threads, and the goal is to, run on a vector of data. And it's similar to the SIMD stuff that we talked about earlier, except instead of like just one instruction where we have it coordinated nicely by the CPU hardware, we're going to then just do that one instruction, perhaps very efficiently. Now we're having a vector of data, and it's processed by the GPU, and the GPU has lots of compute units, and of course we're doing more than just one simple operation at a time. We're doing perhaps several of them individually on each data element, but we have lots and lots of threads on the GPU to do it. So this isn't, of course, the only way to do it. The PlayStation 3, the Cell processor has a heterogeneous architecture. There is a single PowerPC main processor, and then there's 8 SPE, synergistic programming elements, and there is a video linked here, which you may find interesting, to see why it is hard to program for the PS3. It requires a bit of different thinking. It requires you to go a little bit out of your way as compared to what you would normally do when programming for a CPU. For the PS4, things were back to a CPU/GPU type system, although it's not exactly like having a little PC in your living room. But if you wanted to see, the PS3 has the PowerPC core. That's the general purpose computing unit used for most calculations and stuff. And the SIMD coprocessors, those are the ones that are intended to do graphical elements. Ultimately, they're very good at their one specific job. So they are kind of special purpose units, and it's good that they're very good at rendering graphics, because that's what PS3s are for. Okay, you caught me. That's not true. The actual main purpose of the PS3 is installing software updates, because that's sure where it seems to spend all of its time. But hypothetically, it is intended for playing games, sometimes after updates have been installed, maybe, if that ever finishes. Getting aside. The thing we want to get back to, of course, is CUDA, the Compute Unified Device Architecture, and it is NVIDIA's architecture for processing on GPUs. It's our way of telling the GPU, this is what we want, please do it. And it had a C-ish version, C for CUDA, that predates OpenCL. And NVIDIA supports CUDA first and foremost. You can run OpenCL code on their processors, but you may get worse performance. And CUDA is perhaps going to be a bit faster for your hardware. On recent devices, the API allows you to use most C++ features in CUDA code, which you really can't do in OpenCL. OpenCL has a lot more restrictions, and we used to teach that. Again, if you browse in previous versions of the course repository, you could find some information about what we used to do with OpenCL. And unfortunately, although it's not really cross-platform, widely supported, it seems that CUDA has found widespread acceptance in industry. And we used to get some comments from students saying, "Why do we learn OpenCL when it's more likely we would use CUDA in real life?" Okay, fine. They're not so radically different that you couldn't take what you learned from one and put to the other, but still, I think it's pretty clear that CUDA has won. To some extent, that may change in the future, but it seems to be my take on it, at least at this time. Whatever you learn, the principles are similar enough that you can take what you learned in one tool chain and apply it to the other. If you really need cross-platform or you have AMD hardware, as I have in my laptop, then, well, you've got to use OpenCL. That's the way it's done. All right. Now, to give you a high-level overview of the programming model for working with the GPU, it's not very complicated. It's just, the actual devil will be in the details, so to speak. Which is, step one, you're going to write the code for the parallel computation, the kernel, as we call it, separately from the main code. So this is the part, the busy part, the hot loop, where most of your time is going to go. That's the part that you write separately, and we'll come back to that. Then when you're going to run it, you do all your setup, you get your stuff ready. At runtime, you transfer the data that you want the GPU to do to the GPU. In principle, you could execute it on the CPU as well. You wait for the GPU to be finished, and then you transfer the results back when you're done. Okay, that's not too bad. Why do we do this? Well, it makes sense to hand it over to the GPU because there are a lot of cores. Just taking one of the ECE servers in fall 2020, ECE Tesla 2 has a 4-core 3.6 gigahertz CPU, and it has 1,920 CUDA cores, each of which running at 1.8 gigahertz. So each individual core is half the speed, but there are 480 times as many cores available. 200,000 units already, with 1 million more well on the way. You can see, I think, this presents an opportunity for a very significant speed up if the workload that we get is suitable. Suitable has a specific definition, which we will talk about soon enough. It's not amenable to every single kind of problem, but in a lot of cases, this is worth doing. At runtime, there is a significant setup cost for interacting with the GPU and the data transfers. That's both sending work to the GPU to be done and collecting the result. And that does mean there is a significant overhead cost if you want to employ the GPU. But the GPU can get a lot of work done in parallel once it gets going, and so this is why I say it's a bit like deciding to drive or fly. So if the distance that you're traveling is, Ottawa to Montreal, as shown here, Google Maps says that it takes, it's about 200 kilometers, and it takes about 2 hours. If that's the case, then flying makes no sense. You have to get to the airport, you have to get there at least an hour early or so to make your way through the security checkpoints, then you fly, and then you get to the destination airport, and then you have to get from the airport to your final destination. The flying part is fast, but the overhead makes your total average speed just not worth it. On the other hand, if you're going a longer distance, the 4,156 kilometers or so, if you were, going from Waterloo to San Francisco, then driving is way slower. Yes, the overhead of going to the airport remains. You still got to go to the airport. You still got to get there 2 hours early. You get to be touched inappropriately by a security person, customs, immigration, that kind of thing. But once you're in the air, the airplane is moving at like 800 kilometers an hour, and so it takes about 5.5 hours of flying once you're there, making your total travel time, we'll say, 8 or 9 hours for that. Compare that against the 38 or 42 hours of driving that it would take, not even accounting for the fact that at some point you would have to take breaks and may even want to sleep. So it's not something you could do in one shot even if you wanted to, whereas flying you definitely could, and you could even sleep on the way. Okay, so CUDA includes both task parallelism and data parallelism. As we've probably mentioned at least once before, data parallelism is really the central feature. We are evaluating our function, or as it's called in the lingo, a kernel, on a set of points. Each point represents a data element, such as one of the bodies in the n-body simulation, and you could also perform some transformations if you wanted on each pixel of an image or each frame of a video. Something like that would also be well suited to this kind of model. And so if you take that little grid of dots and you consider each of those as being a work item, then we have a two-dimensional problem, which is composed of some number of work items, and each point in there is in what we call the index space. That's the set of points. CUDA also, incidentally, does support task parallelism in that you could run different kernels in parallel, but we're actually not going to talk about that. It's not something that we want to focus on right now, but the option is there if you wish it, and if you have a good reason for why you would want to do that, then by all means, you can. In any case, we'll focus on work items. And a work item is a fundamental unit of work. It is how we tell the GPU, this is a thing I want you to do. And of course, we're going to do that a lot. There's going to be a lot of work to give, so there should be a lot of work items. Otherwise, the overhead of using the GPU is not worth it. Well, they live on an n-dimensional grid, n being up to 3. The previous page had a 2-dimensional work grid. You could have an up to 3-dimensional grid as well, as we will talk about. You get your choice about block size, and this is to say, how many work items get grouped together into a block. You get some input into this. You get some choice. CUDA will potentially spawn a thread for each work item with a unique thread ID, and they're grouped into blocks. Blocks could share memory, and they could work together, but they do have to be able to execute independently if need be, because the system can schedule blocks to run in any order and possibly in parallel. In fact, we want them to run in parallel. We would be disappointed if they didn't, because that's part of the whole benefit of doing something with CUDA is that we are trying to do a lot of things in parallel if we can. You do get some say in block size, and usually I would say to let the system decide. However, for some computations, it's really not that simple, and we might have to specify, in which you will say, look, I want the block size to be this, and that will end up being a big performance improvement over the unmodified version, let's say that. Whatever you choose, and yes, I see that as double F on there, you want to make the best use of the hardware, and so you want to choose for your numbers a multiple of the size of the warp. And warp is what NVIDIA calls a unit of execution in the GPU. There's different names for it. I think the AMD term for it is wavefront. I don't know that they're any different in concept. I think it's just a question of, here it has one name and there it has a different name, but they're fundamentally the same thing as far as we're concerned as users of it. Okay, there's another thing to mention about management of memory, because unlike your typical CPU program, where as far as you're concerned, really all memory is memory and there's not much difference between it, CUDA has memory segmented into a few different types. There are, in fact, 5 of them listed on there. The first one is private memory. So that is available to a single work item. So this is where like local variables would go if you are working on something that's in this work item only, and it can't be shared with anybody else. There are local memory, which is a form of shared memory. So it's shared between work items in the same group. So if you want local items to cooperate, you can do that. It's kind of like a user-managed cache, a workflow where you might use local memory is where you have each group find its own local maximum or its own local minimum, in which case they do have to be able to talk to each other through the shared memory to make that happen. Otherwise, it won't work. There is global memory, and global memory is shared between all work items everywhere, as well as the host. Constant memory is something that resides on the GPU, and it is cached, and it does not change. It is fairly limited in size, so you have to be careful. You can't put a huge input vector into the constant memory, even if the input vector doesn't change. It's just the output vector that changes, because it is limited in that regard. But choose wisely is what I advise. And then there's texture memory. Texture memory is also global memory, and it's also cache, and it potentially provides a very slight speed up over global memory. The GPU has this texture memory for rendering images. You want to play a game, this is a use for texture memory. And it uses it for rendering and interpolating textures, but when you're running the OpenCL or CUDA program, you're not using the texture memory for playing a game. So that memory is still there, and you could still use it if your use case is appropriate. I don't think we're going to do anything that takes advantage of texture memory, but it's there, and we figure that I should mention it because, well, you could in the future have a use case for it where that's actually helpful. Okay, so on top of that, there's the host memory, the RAM in your computer, but we're not really going to think about that too much. As we've seen, there's typically explicit transfer between one place and another. So here's a kernel of my very own. Kernels are written in a variant of C++, so we're going to start with original C++ code, and we're going to convert it to be kernel code. Now, again, void vector add has n for the size of each vector, and we have some floats a, b, and c, and a and b are the input and c is the output. Great, sure, fine, whatever. And for the kernel, what we actually notice is that the loop becomes implicit. The loop induction variable is something we retrieve from the threadIndex.x field. That index is a 3-component vector, so it has x, y, and z dimensions, but this is a linear problem, so we only have the first component, x. We can talk about other things later. We have to add a little prefix here, the global prefix, and we have float A, float B, float C, and so on, but otherwise, C is assigned A at index I plus B at index I. That part is not really that different. Okay, so we should be at least somewhat familiar, I think, with what the language looks like for writing a kernel, because it resembles C++, and hopefully you know at least a little of that. There are a few additions, like the global designation with the underscores on each side of it, really, a large number of features of more recent versions of C++ are now supported in CUDA, and this is actually one of the major advantages over OpenCL, as OpenCL is kind of restrictive in what language features it has. But there are a few things that you can and can't do. What things are permitted will vary significantly based on whichever version of your kernel compiler you have available. So it is the nvcc command, and that is the kernel compiler, and it is the one that will take the kernel and try to turn it into something that can execute on the GPU. If it tells you that something you want to do is not possible, that is a suggestion that says actually the thing you're doing is not supported. I think it is unlikely that we will do anything in this course that will be so exotic enough as to be forbidden by the compiler. If you aren't sure why something is not working or you want to know what's not allowed, there's a link in the notes to the NVIDIA docs that gives you the restrictions. If we encounter one of them in doing an example, I will mention it, but I don't think there were any of those, so I think we will just skip over that. And when we compile the kernel with nvcc, it gets turned into PTX, parallel thread execution instructions. You could think of this as being kind of like assembly, but for the GPU. Can we write our own? Yes. Will we? No. Use the nvcc compiler. In theory, as with assembly instructions, you could imagine it is possible for a true expert to write a better better PTX than the compiler itself could produce. Let's assume that we're not. Another thing that's also helpful is the nvcc compiler will know about what is available on the machine that you're using, what instructions are available, and compile it accordingly. For this reason, it is probably for the best to just let it do that and not sweat about whether a particular instruction or command is supported. By that same token, you should also keep in mind that when you change machines, you want to recompile your nvcc as well. So if yesterday you were working on ECE Tesla 1 and today you're working on ECE Tesla 2, you should recompile to prevent anything where you might encounter an error or unexpected behavior because, oh no, things changed ever so slightly because there's two different compute cards in two different machines. So just keep that in mind. Same thing if you're uploading something that you wrote on your own machine to the ECE servers to execute. Again, please take care to recompile as well. Now, the nvcc compiler has very specific requirements about the underlying compiler upon which it relies. So on ECE Tesla 2, at least at the time when I was making the notes, at the time of writing, nvcc fails if you don't specify running GCC 6 instead of the default. And there's a command nvcc-compiler bin-dir and then user bin gcc-6, and then -ptx, and then nbody.cu is the CUDA file that I want to compile. And if I run the command like that, it will work. So do be careful. Again, if I usually recommend that you test using your using the ECE servers and not your own laptop. If you are working on your own laptop, you might need the matching version of GCC based on what nvcc is expecting, and just running nvcc directly is kind of not advised. I wrote a shell script when I was testing this out, or you could put it in a make file or something, anything that makes it easier so you don't have to type in this long and arcane command every single time. Anyway, when we talk about a kernel, the thing I want to remind you about is that a kernel doesn't necessarily come with any of the guarantees that you get in Rust. There's no niceties that we would usually get that we may now be used to. You can easily read off the end of an array, forget to initialize a variable, allocate memory that you forget to deallocate, that kind of thing. So just because the compiler gives you a pass, it doesn't mean that everything is going to work just as you would expect. Here's an example of something that I got in testing because I got something wrong, and it was thread main panicked it failed to deallocate CUDA device memory illegal address, and this happened actually in the Rust code, but it was a problem that was in the kernel that I wrote. So I needed to correct the kernel, and yeah, that's also a good hint. If you see that there's a panic in CUDA something or other, check carefully to be sure that it's not a problem in the kernel and that your host code, the Rust code, is okay. Could be either one. All right, and I would like to show you now the n-body kernel that I wrote, and we'll also use that when we see how to launch a CUDA program, which we are building up to.